Infinite loop paradoxes, which can be quite fascinating, occur in various fields, including mathematics, philosophy, and computer science. At their core, these paradoxes arise when a situation or a statement leads to a cycle of reasoning that never resolves itself, creating an endless loop of logic. One classic example is the well-known statement, "This statement is false." If the statement is true, then it must be false. But if it is false, then it must be true. This creates a paradox that can leave one pondering the nature of truth and falsehood indefinitely. In computer science, infinite loops can occur in programming when a set of instructions keeps repeating without a clear exit condition. This can happen due to coding errors, where the loop's termination criteria are never met, leading the program to run endlessly. Such loops can consume system resources, causing programs to freeze or crash, which is why understanding and managing them is crucial for developers. In philosophy, infinite loop paradoxes challenge our understanding of concepts like time and causality, leading to discussions about the nature of existence and reality itself. The implications of infinite loops extend into our daily lives as well. They can manifest in situations where decisions or actions lead back to the same starting point, causing frustration and confusion. For instance, one might find themselves in a cycle of procrastination, where the desire to start a task leads to endless distractions, which ultimately leads back to the same task that remains unfinished. This cyclical nature can be seen as a metaphor for broader human experiences, prompting reflection on how we approach challenges and problem solving. In summary, infinite loop paradoxes, with their intriguing complexities, invite exploration into the nature of logic, existence, and human behavior, revealing the often perplexing and cyclical patterns that can emerge in thought, technology, and life itself. Infinite loop paradoxes, those intriguing puzzles that challenge our understanding of logic and infinity, have a rich history that weaves through philosophy, mathematics, and even computer science. The origins of these paradoxes can be traced back to ancient philosophers, who first grappled with the concept of infinity. One of the earliest known examples is found in the works of Zeno of Elea, a Greek philosopher from the 5th century BCE. Zeno proposed several paradoxes, the most famous being the Achilles and the tortoise, which illustrates a scenario where Achilles, a swift runner, can never overtake a tortoise that has a head start, because every time he reaches the point where the tortoise was, the tortoise has moved a little further ahead. This paradox raises fundamental questions about motion, space, and the nature of infinity, setting the stage for future discussions. Fast forward to the early 20th century, where mathematicians like George Cantor began developing set theory and the concept of different sizes of infinity. Cantor's work revealed that some infinities are larger than others, which led to deeper explorations into the properties of infinite sets. His famous diagonal argument presents a paradox regarding the real numbers, suggesting that it is impossible to list all real numbers in a sequence, because any such list can always be expanded by creating a new number, which leads to the conclusion that the set of real numbers is uncountably infinite. This revelation opened up new avenues of thought and introduced the idea of infinite loops in a mathematical context. As these philosophical and mathematical discussions evolved, they began to intersect with logic. In the early 20th century, the development of formal logic by figures like Bertrand Russell and Kurt Gödel further complicated the landscape of paradoxes. Russell's paradox, which questions whether the set of all sets that do not contain themselves contains itself, exposes a fundamental flaw in naive set theory, leading to a deeper understanding of self-reference and the implications of infinity. Gödel's incompleteness theorems, articulated in the 1930s, illustrate that in any sufficiently powerful logical system, there are statements that cannot be proven or disproven, hinting at the limitations of formal systems and the potential for infinite regress in logical reasoning. In more recent times, the rise of computer science has brought new life to the study of infinite loop paradoxes, particularly through the lens of algorithms and programming. Concepts like infinite loops in programming, where a set of instructions repeats endlessly. Infinite loop paradoxes in philosophy present fascinating scenarios that challenge our understanding of logic, reality, and self-reference. One of the most famous examples is the liar paradox, which arises from a simple statement. This statement is false. If the statement is true, then it must be false. But if it is false, it must be true, creating a loop that defies resolution. This paradox digs deep into the foundations of truth and language, posing questions about how we define and understand these concepts. Another intriguing example is the barber paradox, which features a barber who shaves all and only those men who do not shave themselves. The paradox emerges when we ask whether the barber shaves himself. If he does, according to the rule, he must not shave himself, but if he doesn't, then he must shave himself, leading to a perplexing situation that illustrates the complexities of self-reference. A related paradox is the Russell's paradox, which deals with sets and their members. Imagine a set that contains all sets that do not contain themselves. If such a set exists, it leads to the question of whether it contains itself. If it does, then it contradicts its own definition, yet if it does not, then it must contain itself. This paradox highlights issues in set theory and has significant implications for the foundations of mathematics and logic. The Cretic paradox, originating from the statement of a Cretan who declares that all Cretans are liars, adds another layer to the discussion. If the statement is true, then the speaker, being a Cretan, must also be lying, which makes the statement false. This paradox challenges our understanding of identity and truthfulness within cultural contexts. Moreover, the self-referential paradox appears in various forms across literature and philosophy, showcasing scenarios where a statement refers back to itself. For example, consider a sentence that says, "This sentence is false." This self-reference creates a loop, leading to confusion about the truth value of the statement, which is central to discussions in both philosophy and logic. Philosophers have also explored the Grelling-Nelson paradox, which involves adjectives. It asks whether the term heterological, which describes words that do not apply to themselves, is heterological. If it is, then it does not apply to itself. But if it is not, then it must apply to itself. This paradox emphasizes the complexities inherent in language. Infinite loop paradoxes often engage our minds in fascinating ways, especially when we explore the role of self-reference within them. Self-reference occurs when a statement refers to itself, creating circular definitions or scenarios that can lead to contradictions. One classic example is the famous liar paradox, which presents a statement like, "This statement is false. If the statement is true, then it must be false. But if it is false, then it must be true," resulting in an endless loop of reasoning that confounds our understanding. This kind of self-reference is not just a playful exercise in logic. It has profound implications in various fields, including philosophy, mathematics, and computer science. In mathematics, self-reference can lead to paradoxes in set theory, such as the well-known Russell's paradox, which questions whether a set that contains all sets that do not contain themselves can exist without contradiction. Here, self-reference creates a loop that challenges our foundational understanding of sets and their relationships. In computer science, self-referential structures can be both a tool and a source of complexity, especially in recursive functions, where a function calls itself to solve a problem, potentially leading to infinite loops if not carefully managed. These loops can crash programs or lead to incorrect outputs, demonstrating how self-reference can be both powerful and perilous in computational contexts. Moreover, self-reference is also a crucial element in language and meaning, where statements can refer to their own structure, leading to complexities in semantics and interpretation. For instance, consider the sentence, "This sentence contains 5 words," which is a simple but effective example of self-reference. Here, The sentence describes itself, and its truth can be easily verified. Unlike the more convoluted paradoxes, this interplay between self-reference and meaning shows how language can create loops that both enrich and complicate our communication. The exploration of self-reference in infinite loop paradoxes not only highlights the nuances of logical reasoning, but also invites us to question the limits of our understanding, pushing the boundaries of how we think about truth, language, and the concepts that underpin our reality. Gödel's incompleteness theorem, which was developed by the mathematician Kurt Gödel in the early 20th century, is a fascinating concept that fundamentally changed our understanding of mathematics and logic. This theorem revolves around the idea that within any consistent mathematical system, there are statements that cannot be proven or disproven using the rules and axioms of that system. In simpler terms, no matter how complete you think your mathematical framework is, there will always be some truths that remain elusive, hidden in the shadows of complexity. This theorem suggests that there are limits to what can be known, and it challenges the notion of absolute certainty in mathematics, as it shows that some propositions are true but cannot be proved within that system. One of the most intriguing implications of Gödel's work is its connection to the concept of infinite loops, particularly in computer science and logic. An infinite loop occurs when a sequence of instructions, whether in a mathematical proof or a computer program, continues indefinitely without reaching a conclusion. This can happen in various contexts, such as when a program is designed to repeat a set of actions until a certain condition is met, but that condition is never fulfilled, leading to endless repetition. This connection between Gödel's theorem and infinite loops is not merely theoretical. It has practical implications for computer programming and algorithm design. For instance, in programming, encountering an infinite loop can cause a system to crash or become unresponsive, which is a challenge that programmers often face. The idea of infinite loops also ties back to Gödel's theorem through the lens of formal systems. Just as a mathematical statement might loop back on itself without resolution, so too can algorithms become trapped in cycles of execution that yield no output. This intersection of mathematics, logic, and computing provides a rich ground for exploration, as it highlights the complex relationship between truth, proof, and computational processes. It invites us to consider deeper questions about the nature of knowledge and the limits of what we can understand, not just in mathematics, but in various fields of inquiry. The implications of Gödel's work extend beyond pure mathematics and into philosophy, encouraging us to ponder the boundaries of human understanding and the inherent uncertainty that comes with exploring the infinite. As we delve into these topics, we can appreciate the intricate connections between different domains of knowledge, recognizing that the quest for understanding is often filled with paradoxes and unresolvable questions, reminding us of the beauty and mystery that nature and, indeed, all of existence holds. The Barber paradox is a fascinating, logical puzzle that touches on the realms of set theory and self-reference, and it invites us to ponder the nature of truth and contradiction. Imagine a town with a barber who shaves everyone who does not shave themselves. Now, here's the paradox. Does the barber shave himself? If he does shave himself, then according to the rule, he should not be shaving himself, since he only shaves those who do not shave. Conversely, if he does not shave himself, then he must shave himself, because he shaves everyone who doesn't shave. This creates a loop of reasoning that cannot be resolved, illustrating a fundamental problem in set theory related to self-reference and definitions. This paradox was introduced by the philosopher and mathematician Bertrand Russell, and it serves as a critical example in discussions about logic and mathematics. The Barber paradox is significant because it reveals limitations in our understanding of sets and can be related to other famous paradoxes, such as Russell's paradox, which questions whether a set can contain itself. These logical puzzles challenge us to think critically about definitions, categories, and the rules we create in mathematics and logic, pushing us to understand deeper implications of self-reference and infinity. Beyond academic interest, the Barber paradox has implications in philosophy, computer science, and even artificial intelligence, where self-reference and recursive definitions are prevalent. It raises questions about how we define rules and boundaries, and what happens when those definitions intersect in unexpected ways. By exploring such paradoxes, we gain insight into the nature of truth, the limits of language, and the complexities of reasoning itself, revealing how sometimes, the more we try to categorize and define, the more elusive the truth can become. This paradox serves as a reminder that in our quest for knowledge, we must navigate the intricacies of logic and language with care, as the simplest of scenarios can sometimes lead to the most profound questions. The liar paradox is a fascinating concept in philosophy and logic, often encapsulated in the simple statement, "This statement is false." When we encounter this statement, we are immediately drawn into a web of contradiction, because if the statement is true, then it must be false, but if it is false, then it must be true. This paradox reveals much about the nature of truth and language, demonstrating how language can sometimes lead us into infinite loops of reasoning that defy straightforward understanding. The implications of the liar paradox extend beyond mere wordplay. They challenge our fundamental assumptions about truth, meaning, and the structure of logical reasoning itself. Philosophers have debated this paradox for centuries, with various interpretations and solutions proposed, yet it remains unresolved in many respects. Some suggest that the paradox arises from self-reference, where a statement refers to itself, creating a complex interplay between truth and falsehood. Others argue that it highlights limitations in our language and logical systems, prompting us to reconsider how we define truth in a broader context. The concept has even made its way into discussions about mathematics and computer science, where similar self-referential constructs can lead to complications in algorithms and programming. Additionally, the liar paradox invites us to explore deeper philosophical questions about the nature of reality and how we communicate our understanding of it. This paradox can be viewed as a reflection of the complexities inherent in human thought and language, reminding us that not all questions have clear-cut answers, and some may lead us into infinite loops of contemplation, shedding light on the intricate tapestry of knowledge and belief. The infinite nature of the liar paradox serves as a metaphor for the endless pursuit of understanding, pushing the boundaries of our inquiry and encouraging us to engage with ideas that challenge our perceptions of truth and reality. In exploring this paradox, we are drawn into a rich landscape of philosophical thought, where questions often lead to more questions, and the journey of inquiry becomes as significant as the answers we seek. Zeno's paradoxes, originating from ancient Greece, present fascinating puzzles that challenge our understanding of motion, space, and time, capturing the interest of philosophers and mathematicians alike for centuries. One of the most famous of Zeno's paradoxes is Achilles and the tortoise, where Achilles, a swift warrior, races against a slow-moving tortoise. In this scenario, Achilles gives the tortoise a head start. Zeno argues that before Achilles can reach the tortoise, he must first cover the distance to where the tortoise began. However, by the time Achilles reaches that point, the tortoise has moved ahead, creating an endless series of distances that Achilles must cover, suggesting that he can never catch the tortoise, despite being much faster. This paradox raises questions about infinite divisibility, as Zeno suggests that space and time can be divided into infinitely small parts, leading to seemingly impossible conclusions about motion. Another paradox, the dichotomy paradox, illustrates a similar concept. Here, Zeno argues that before one can run a certain distance, they must first reach the halfway point. But before reaching that halfway point, they must cover a quarter of the distance, then an eighth, and so on, creating an infinite sequence of steps. This leads to the conclusion that motion is impossible, as one can never complete an infinite number of tasks in a finite time. These paradoxes highlight the complexities of understanding infinity, as they challenge our intuitions about how we perceive distance and motion. In modern mathematics, the resolution of Zeno's paradoxes is approached through the concept of limits and calculus, where mathematicians have demonstrated that an infinite series can converge to a finite value. For example, in the case of Achilles and the tortoise, if the distances are halved repeatedly, the sum of these distances can equal a finite amount of time that Achilles takes to overtake the tortoise. This mathematical framework shows that even though there are infinitely many points along the way, the total time taken to complete the journey can still be finite. Zeno's paradoxes have not only influenced mathematics but have also sparked discussions in physics, particularly in understanding concepts like space-time and the nature of continuity. The debates around these paradoxes have led to various interpretations in philosophy, with some philosophers arguing that our understanding of motion and time must be re-examined in light of Zeno's challenges. The exploration of these ideas continues to be relevant, as it encourages deeper inquiry into Cantor's paradox, which emerges from the realm of set theory, reveals some truly fascinating aspects of infinite sets, and it challenges our understanding of infinity itself. At its core, Cantor's paradox arises from the work of mathematician George Cantor, who showed that not all infinities are created equal, and that certain infinite sets can be larger than others. For instance, the set of all real numbers is larger than the set of all natural numbers, even though both sets are infinite. This concept leads us to consider the implications of forming a set of all sets, which creates a logical dilemma. When we attempt to construct a set of all sets, we quickly encounter contradictions. If this set contains itself, then by definition, it must also contain all sets that do not contain themselves. This creates a paradox, as it leads to an endless loop of self-reference and contradiction. To put it simply, if the set contains itself, it must not contain itself, and if it does not, then it must contain itself, which makes it impossible to define. This paradox highlights the limitations and complexities involved in dealing with infinite quantities. Moreover, Cantor's work led to the development of different sizes of infinity, a concept that many find mind-boggling. For example, while the natural numbers can be counted, the real numbers between any two natural numbers cannot be counted in the same way, as there are infinitely many of them. This leads us to consider the continuum hypothesis, which posits that there is no set whose size is strictly between that of the integers and the real numbers. This hypothesis remains one of the most famous unsolved problems in mathematics, illustrating just how deep and intricate the nature of infinity can be. Cantor's paradox also has implications beyond pure mathematics. It touches upon philosophy, logic, and even computer science. For instance, in computer science, understanding infinite sets can help in the development of algorithms and data structures that deal with infinite data, which is essential in fields like artificial intelligence and machine learning. As we delve deeper into the paradox, we see that it not only challenges our understanding of mathematics, but also invites us to think critically about the nature of existence, reality, and abstraction. The concept of infinity, especially when combined with the paradoxes presented by Cantor, encourages us to explore the boundaries of human thought and comprehension. It raises questions about the nature of mathematical truths and how we perceive and categorize infinity. Pushing quantum mechanics, a fascinating branch of physics, delves into the behavior of matter and energy at incredibly small scales, often leading to surprising and counterintuitive phenomena. One such intriguing idea is the concept of infinite loops, which can be metaphorically connected to various processes in quantum mechanics. In this realm, particles can exist in multiple states at once, a phenomenon known as superposition, which creates a kind of loop in possibilities, where the outcomes are not fixed until they are observed. This idea leads us to think about how, in quantum systems, time and causality may not follow the straightforward paths we assume in our everyday experiences. Theoretical frameworks, like the idea of a quantum computer, utilize these principles to perform calculations in ways that classical computers cannot, allowing for the possibility of looping through calculations at extraordinary speeds, thus presenting a kind of infinite loop in computational processes. Furthermore, the notion of entanglement, another key aspect of quantum mechanics, introduces a kind of connection between particles that transcends traditional space and time, creating loops of interaction that can be instantaneous, regardless of distance. This suggests that the relationships between particles are not linear, but rather form complex networks, which can be thought of as loops of influence, where the state of one particle can affect another instantaneously, creating a web of interconnectedness that challenges our understanding of time. Some physicists also explore theories of quantum gravity, which attempt to unify quantum mechanics with general relativity, hinting at the possibility of loops in the very fabric of space-time itself, where time could be cyclical rather than linear, leading us to ponder the nature of the universe in a way that is both mind-bending and deeply philosophical. These ideas, while still theoretical, open up a myriad of questions about the nature of reality, the structure of time, and the potential for infinite possibilities, all stemming from the fundamental principles of quantum mechanics, which continue to inspire both scientists and thinkers alike. The implications of these concepts stretch far beyond the laboratory, influencing fields such as philosophy, technology, and our understanding of consciousness, as we begin to realize that the universe may not be as straightforward as it seems, but rather a complex, intertwined system where infinite loops of potential and interaction are a fundamental part of existence. Time travel has fascinated people for centuries, inspiring countless stories, movies, and theories. But the concept also brings up complex ideas, including the notion of infinite loop paradoxes. Imagine, for a moment, a traveler who journeys back in time, perhaps to witness a historical event, or even to meet a famous figure from the past. However, as they interact with the past, they might inadvertently change something significant, leading to a reality that is different from the one they originally came from. This scenario raises many intriguing questions, one of which is the famous grandfather paradox. In this paradox, if a time traveler goes back in time and prevents their grandfather from meeting their grandmother, the time traveler would never be born, which leads to a logical impossibility. How could they have gone back in time in the first place? This paradox invites us to think about the nature of time and causality, and it opens up discussions about different theories of time travel. Some scientists suggest that time might not be linear, and that all moments exist simultaneously in a sort of block universe, where altering one event does not necessarily change the entire timeline. This leads to the idea of multiple timelines or parallel universes. So if a time traveler changes something in the past, they might create a new branch of reality, while the original timeline continues to exist unchanged in another universe. Moreover, the infinite loop paradox is another fascinating concept related to time travel. In an infinite loop, events repeat themselves endlessly, creating a cycle where the actions of the time traveler lead to the very circumstances that send them back in time in the first place. For instance, imagine a scenario where a time traveler tries to prevent a disaster, but in doing so, they inadvertently cause it. This creates a loop where the traveler is stuck in a cycle of events, unable to change the outcome. It's a mind-bending idea, but it challenges our understanding of free will and destiny. Theoretical physicists have explored these concepts further, using mathematics and the laws of physics to analyze the possibilities of time travel and its consequences. Some theories propose that wormholes, which are hypothetical passages through space-time, could allow for time travel, while others suggest that traveling faster than light might be necessary to achieve such feats. As these theories evolve, so too does our understanding of time itself. Philosophers, scientists, and writers continue to debate the implications of time travel, and while it remains a topic of speculation, it encourages us. The bootstrap paradox, often a topic of fascination in the realms of science fiction and theoretical physics, raises intriguing questions about time travel, causality, and the nature of existence. Imagine a scenario where you receive a book, a detailed manual on time travel, from a future version of yourself. You read this book, and then, years later, you create the very book you received. But here's the twist. The author of the book has no known origin, as it seems to exist without being created in the conventional sense. This is the essence of the bootstrap paradox, where an item or information appears to be self-originating, leading to questions about the linearity of time. In the context of nature, one might draw parallels to the concept of ecosystems, where various species depend on one another in a seemingly endless cycle of life. However, unlike the paradox, these relationships are often rooted in evolutionary history, rather than a time loop. Consider a case study involving time travel, where a scientist, determined to alter a significant event in the past, travels back in time to a moment he believes will change the future for the better. However, as he interacts with the past, he inadvertently sets off a chain of events that leads to the very future he was trying to prevent, creating a loop that is incredibly difficult to break. This scenario mirrors the bootstrap paradox, as the actions taken in the past directly influence the future, which then influences the past, creating a self-sustaining cycle. Such thought experiments can lead to deeper philosophical questions about free will, destiny, and the nature of time itself, engaging both scientists and philosophers alike. In literature and film, the bootstrap paradox often serves as a fascinating plot device, inviting audiences to ponder the implications of time travel on their understanding of reality. Works like Back to the Future and Harry Potter and the Prisoner of Azkaban illustrate how characters navigate the complexities of time, often facing the consequences of their actions in unexpected ways. This narrative technique not only captivates viewers, but also encourages them to think critically about the idea of causality and how our choices can reverberate through time, just as ecological interactions can have long-lasting effects on the environment. The paradox also invites comparisons to natural phenomena. For instance, consider the concept of energy in closed systems, where energy is neither created nor destroyed, but rather transformed. This principle echoes the bootstrap paradox, as elements in nature like water cycling through infinite loops in computability theory present fascinating implications that stretch across various domains of mathematics and computer science, revealing deep insights into how we understand algorithms and their limitations. At the heart of computability theory lies the concept of a Turing machine, which models the way a computer processes information. When a Turing machine enters an infinite loop, it continues to execute instructions endlessly without reaching a conclusion. This phenomenon raises critical questions about what it means for a problem to be solvable. If a problem cannot be resolved within a finite number of steps, it becomes essential to analyze the nature of the problem itself, as well as the algorithms designed to solve it. For instance, consider the famous halting problem, which states that there is no general algorithm that can determine whether a given program will eventually halt or run forever. This implies a fundamental limitation in our ability to predict the behavior of certain algorithms, leading to a richer understanding of both theoretical and practical computing. When studying these infinite loops, researchers often explore their connection to decidability, a key concept that helps categorize problems based on whether they can be algorithmically solved or not. The existence of infinite loops suggests that some problems lie outside the realm of what can be computed, leading to a classification of problems as either decidable or undecidable. Moreover, infinite loops can impact performance in real-world applications, where a program caught in an endless cycle may consume resources indefinitely, potentially leading to system crashes or failures. This aspect emphasizes the importance of error handling and debugging in software development, as developers must design systems that recognize and manage infinite loops effectively. Understanding these implications not only helps in creating more robust algorithms, but also in improving the overall efficiency of computing systems. In addition, infinite loops challenge our philosophical understanding of computation. They invite contemplation about the nature of time and infinity, within the realm of algorithms, as well as the limits of human knowledge. Can we ever fully comprehend the infinite structures that arise from computation? This question resonates with mathematicians and computer scientists alike, reflecting a blend of curiosity and caution as we explore the boundaries of what can and cannot be computed. As we delve deeper into infinite loops, we must also consider their educational implications. Teaching students about infinite loops and their consequences encourages critical thinking and problem-solving skills, as they learn to identify potential pitfalls in algorithm design. By engaging with these complex ideas, learners are better prepared to tackle challenges within the field of computer science, fostering a mindset that values both creativity and analytical reasoning. The exploration. In the realm of programming, recursive functions and infinite loops are two fundamental concepts that can both perplex and fascinate those eager to learn about the inner workings of code. A recursive function is a function that calls itself in order to solve a problem. Imagine you have a task, like calculating the factorial of a number, which is the product of all positive integers up to that number. A recursive approach to this task would involve the function calling itself with a smaller number each time, until it reaches the base case, which is usually the simplest instance of the problem, such as the factorial of 0 being 1. This method can be elegant and concise, allowing programmers to express complex logic in a straightforward manner. However, recursion has its limits. If the function calls itself too many times without reaching a base case, it can lead to a stack overflow, causing the program to crash. On the other hand, infinite loops occur when a set of instructions in a program repeats endlessly without a condition being met to stop it. This can happen if the loop's condition is never satisfied, or if there is no exit condition at all. While infinite loops can be useful in certain scenarios, such as creating a server that continuously listens for requests, they often lead to problems if not managed carefully. For example, if a programmer accidentally creates an infinite loop while attempting to process a list of items, the program may freeze or become unresponsive, consuming resources and potentially crashing the system. Thus, understanding both recursion and infinite loops is crucial for anyone looking to delve deeper into programming. Now, when we think about these concepts in nature, we can draw intriguing parallels. Just as recursive functions rely on their own definitions to achieve a solution, many natural processes display a form of recursion. For instance, consider the growth patterns of certain plants, where the branching of a tree mimics a recursive structure, each branch leading to smaller branches, much like how a recursive function breaks down a problem into smaller parts. Similarly, infinite loops can be seen in certain ecological systems, where populations can grow exponentially if conditions are ideal, leading to cycles that may seem never-ending until some external factor interrupts the cycle. This fascinating intersection of programming logic and natural phenomena invites learners to explore the connections between the digital world and the environment. By understanding these concepts, one not only enhances their programming skills, but also gains insights into the intricate patterns and processes that govern nature itself. The beauty of recursion and the caution needed with infinite loops reflect the delicate balance found. The relationship between infinite loops and fractals is a fascinating intersection of mathematics and nature, revealing deep connections that can be both beautiful and complex. Infinite loops, in a computational sense, occur when a set of instructions continues to execute without ever reaching a conclusion, often leading to endless repetition. These loops can be visualized in many ways, but one of the most intriguing aspects is how they can reflect certain patterns found in fractals, which are geometric shapes that can be split into parts, each of which is a reduced-scale copy of the whole, a property known as self-similarity. Fractals are not just abstract mathematical constructs. They are present in various forms throughout nature, from the branching of trees and the structure of snowflakes to the coastlines of islands. Infinite loops, in the context of fractals, can be observed in the iterative processes used to create these stunning designs. For instance, the Mandelbrot set, one of the most famous fractals, is generated through a simple iterative formula, where each point is calculated based on the values of the points surrounding it. This process can continue infinitely, creating complex patterns that are both intricate and mesmerizing. Moreover, the relationship extends beyond mere mathematical curiosity. It touches on the concept of chaos theory, which studies how small changes in initial conditions can lead to vastly different outcomes. In fractals, this is evident as you zoom in on the intricate details of a fractal shape. The patterns continue to emerge without ever repeating exactly, much like how an infinite loop can produce endless outcomes based on its initial instructions, but without a definitive endpoint. In nature, this connection can be seen in the way certain natural phenomena unfold. For example, the growth patterns of certain plants, such as ferns, exhibit fractal characteristics, where the leaves branch out in a self-similar manner. If one were to observe the process of growth, one might imagine a sort of infinite loop where each new leaf's growth is dependent on the conditions and development of the previous ones, creating a cycle that seems endless. Additionally, the concept of infinite loops can also be related to the idea of recursion, which is prevalent in both programming and natural systems. In mathematics, recursion allows for the definition of a function in terms of itself, creating layers upon layers of complexity that can be visualized through fractals. This relationship illustrates how both concepts, while rooted in different disciplines, share a common thread of continuity and complexity. Infinite loop paradoxes in literature create fascinating puzzles. Capturing the imagination of readers and writers alike, they challenge our understanding of time, narrative structure, and reality, often leading to mind-bending twists that make us question our perceptions. One of the most famous examples can be found in Jorge Luis Borges' short story, The Garden of Forking Paths, where the concept of time is not linear, but rather a series of diverging paths, each representing different choices and outcomes. This story invites readers to consider how every decision branches into a multitude of possibilities, creating an infinite loop of narratives that overlap and intertwine. Similarly, in Kurt Vonnegut's Slaughterhouse-Five, the protagonist, Billy Pilgrim, becomes unstuck in time, experiencing moments from his life in a non-linear fashion, from his time as a soldier in World War II to his encounters with aliens, creating a narrative that loops back on itself, emphasizing the idea that time is not just a straight line, but a complex web of experiences. Another intriguing example lies in the works of David Foster Wallace, especially in Infinite Jest, where the narrative is filled with footnotes and digressions that create a sense of looping and recursion. The reader often finds themselves navigating through a maze of thoughts and stories that reflect the complexity of human experience, while also presenting the challenge of addiction and entertainment in modern society. The use of infinite loops in literature not only serves as a stylistic device, but also encourages readers to reflect on deeper themes, such as fate, free will, and the nature of reality, as seen in the renowned novel Catch 22 by Joseph Heller, where the protagonist, Yossarian, is trapped in a circular logic of military bureaucracy, creating a paradox that highlights the absurdity of war and the struggles of individuals against an unyielding system. In science fiction, infinite loops often explore the implications of time travel, as seen in works like The Time Machine by H.G. Wells or 11,022,063 by Stephen King, where characters find themselves facing the repercussions of their actions across different timelines, leading to complex scenarios that can have no clear resolution. These narratives captivate readers, drawing them into a world where cause and effect become entangled, and the boundaries of time blur, creating a sense of wonder and unease. In addition to time travel, infinite loops can also manifest in themes of reincarnation, as seen in Cloud Atlas by David. The infinite monkey theorem is a fascinating concept that explores the nature of randomness and probability. It suggests that if you had an infinite number of monkeys typing randomly on typewriters for an infinite amount of time, they would eventually produce the complete works of Shakespeare, or any other text, purely by chance. This idea, while seemingly absurd at first glance, highlights the principles of randomness, as well as the laws of probability, which govern how likely certain outcomes are in a given situation. Randomness plays a crucial role in many aspects of nature, from the genetic variations that lead to evolution to the unpredictable patterns of weather, which can often feel chaotic, yet still obey underlying physical laws. Now, let's consider how randomness is inherent in nature and how it affects the world around us. For example, the process of natural selection relies on random mutations occurring in an organism's DNA. These mutations can be beneficial, harmful, or neutral, and over time, those that provide an advantage in a given environment may lead to a species thriving, while others may fade away. Similarly, in ecology, the distribution of species within an ecosystem can often appear random, but is influenced by a complex interplay of factors such as climate, geography, and interactions among species, which can create a rich tapestry of life, seemingly random, yet deeply interconnected. In addition, randomness is also evident in the phenomenon of genetic drift, which is a mechanism of evolution that occurs due to chance events that can cause certain alleles to become more or less common in a population. This process can lead to significant changes over generations, particularly in small populations, where random events can have a larger impact. Think about how a natural disaster, such as a flood or a fire, can randomly eliminate certain individuals from a population, which might lead to unexpected shifts in genetic diversity, shaping the future of that species in unforeseen ways. Furthermore, randomness influences the patterns we observe in the natural world, whether it's the intricate designs of snowflakes, which form through random processes of freezing water molecules, or the distribution of stars in the universe, which seems random but is governed by the laws of physics and gravity. Even in the realm of quantum mechanics, the behavior of particles can appear random, challenging our understanding of determinism and causality, leading to fascinating discussions about the nature of reality itself. The infinite monkey theorem, thus, serves as a thought experiment that invites us to ponder the role of chance in our universe, and how, amidst infinity, plays a crucial role in both calculus and analysis, acting as a bridge between the finite and the limitless, influencing our understanding of concepts like limits, continuity, and convergence. In calculus, the idea of infinity emerges when we deal with limits, particularly when we analyze the behavior of functions as they approach certain points, or as they extend toward infinity. For instance, when we say that the limit of a function approaches infinity, we imply that the function's values grow larger and larger without bound, which allows us to understand how functions behave at extreme values, leading to insights about asymptotic behavior and the overall shape of graphs. In the context of integration, infinity becomes significant when we discuss improper integrals, where we integrate over an infinite interval, or where the function itself approaches infinity at certain points. This allows us to calculate areas under curves that extend indefinitely, broadening the scope of what we can analyze and understand in mathematics. The convergence or divergence of these integrals often hinges on how a function behaves as it approaches infinity, leading mathematicians to develop criteria for determining whether an infinite sum or an infinite area can be assigned a finite value. Moreover, in the realm of sequences and series, infinity is integral to understanding convergence. A sequence can converge to a limit as the number of terms approaches infinity, and this concept is foundational in calculus, forming a basis for more complex analyses, including Taylor series and Fourier series. Each term in these series reveals patterns and behaviors of functions that can be understood in terms of their limiting behavior, further emphasizing the importance of infinity in mathematical analysis. The concept of infinity also challenges our intuition, prompting questions about the nature of size, continuity, and the continuum itself. For example, George Cantor's work on different sizes of infinity introduced the idea that not all infinities are equal, Some infinities are larger than others, leading to a deeper understanding of the continuum and the set of real numbers. This has profound implications in various fields, including set theory, topology, and even the philosophy of mathematics, where the notion of infinity raises questions about the foundations of our mathematical framework. Additionally, in real analysis, infinity allows us to explore the concept of limits more deeply, leading to the formal definition of continuity, where a function is continuous if it does not jump or have breaks as we approach a point, including at points approaching infinity. This understanding is essential for developing a rigorous approach to calculus, as it provides the tools needed to analyze functions in exploring the moral implications of infinite loop scenarios. It's essential to consider how such situations can challenge our understanding of decision-making, responsibility, and ethical behavior. Infinite loops, often discussed in philosophical debates and theoretical frameworks, refer to situations where a series of actions or decisions lead back to the original state, creating a cycle with no clear resolution. These scenarios can be applied to various contexts, from storytelling in literature to dilemmas faced in real life, such as environmental issues, social justice, and even technology. For example, in an infinite loop scenario where a community continually debates how to reduce pollution, yet each proposed solution leads to unforeseen consequences, we are prompted to question the effectiveness of our actions. The moral implication here is significant. It forces us to confront whether our intentions align with the outcomes of our decisions. Are we genuinely working towards a solution, or are we merely perpetuating a cycle of inaction? This dilemma can lead to moral distress, as individuals and communities grapple with the weight of their choices and the realization that sometimes, despite our best efforts, we may not be able to break free from harmful patterns. Additionally, when we consider infinite loops in the context of technology, such as algorithms that perpetuate bias or misinformation, the moral implications become even more pronounced. Here, we must reflect on accountability. If a system continuously produces harmful outcomes, who is responsible for these consequences? The designers, the users, or the technology itself? This question echoes throughout discussions of ethics in artificial intelligence, where the stakes include not just individual lives, but the fabric of society itself. The implications of such scenarios are profound, compelling us to think critically about the systems we create and the long-term effects they may have. Moreover, infinite loop scenarios can also highlight the importance of perspective in moral reasoning. When faced with a looping situation, different stakeholders may have varying viewpoints on what constitutes a moral action. For instance, in environmental conservation, the debate between economic development and ecological preservation often leads to a cyclical argument where each side presents valid concerns. This results in a loop where solutions are proposed, yet disagreements halt progress. The moral implications here involve understanding the complexities of each position and seeking a balanced approach that respects diverse values and needs. Furthermore, the concept of infinite loops can serve as a metaphor for personal growth and ethical development. Individuals might find themselves in a loop of repetitive behavior, struggling to make meaningful changes in their lives or communities. This introspection can lead to a deeper understanding of one's. In the realm of game theory, infinite loop paradoxes present intriguing challenges, as they involve scenarios where players find themselves caught in endless cycles of decision-making, leading to outcomes that can seem perplexing or counterintuitive. This phenomenon often arises in games where players must make choices based on the expected behavior of others, resulting in situations where the strategies lead back to the original state, creating a loop. One well-known example is the prisoner's dilemma, where two players must decide whether to cooperate or betray each other, but the optimal decision can lead to a situation where neither player can escape the cycle of mistrust, ultimately harming both. Another instance can be seen in repeated games, where players interact multiple times, and their strategies evolve based on previous encounters. The dilemma here lies in the fact that if both players continually focus on short-term gains, they may end up in a loop of betrayal, rather than cooperating for a mutually beneficial outcome. This paradox can be illustrated through the concept of trembling hands, where players might mistakenly choose a suboptimal strategy, leading to unpredictable results and potentially trapping everyone in a less favorable situation. Moreover, infinite loops can also appear in auction settings, where bidders may engage in endless rounds of bidding, each trying to outsmart the other, only to find themselves driving the price far beyond the item's actual value. This behavior can stem from psychological factors, such as the desire to win or fear of losing. As players become increasingly competitive, they may end up in a loop of escalating bids, leading to a situation where the auction becomes a war of attrition rather than a rational economic transaction. In addition, the concept of mixed strategies in game theory can contribute to infinite loops as well. When players randomize their choices to keep opponents guessing, it can lead to cycles where no player can predict the other's moves, creating a dynamic that feels like a continuous loop of uncertainty. The outcome becomes less about finding a definitive strategy and more about navigating the complexities of player psychology and behavior. Furthermore, the evolution of strategies in evolutionary game theory can highlight infinite loop paradoxes as well, as populations of players adapt their strategies over time. Sometimes, these adaptations can lead to stable states where certain strategies dominate, but in other cases, they can result in oscillations or cycles that never settle into a clear equilibrium. This dynamic nature of strategy evolution illustrates how, even in a structured framework, unpredictability can lead to paradoxical outcomes. In conclusion, eternal recurrence is a fascinating concept that has intrigued philosophers, scientists, and thinkers for centuries. At its core, it suggests that the universe and everything within it may repeat itself infinitely, with every event, every choice, and every experience occurring over and over again in exactly the same way. This idea raises profound questions about existence, meaning, and how we perceive time. If one were to accept the notion of eternal recurrence, it could lead to a different understanding of our daily lives. Imagine if every moment we live, every joy we feel, and every sorrow we experience were to happen again, endlessly. Would we approach our lives differently? Would we make the same choices? Or would we strive to live as fully as possible, knowing that every action counts for eternity? This leads us to ponder the significance of our actions, as each decision might hold greater weight if it were to echo through time forever. Philosophers like Friedrich Nietzsche have famously explored this concept, suggesting that embracing the idea of eternal recurrence could lead to a more vibrant and passionate existence. He argued that if one could affirm life so completely as to welcome the idea of reliving it in its entirety, it would signify a deep acceptance of oneself and one's circumstances. This acceptance could foster resilience, encouraging individuals to face challenges with a renewed sense of purpose as they ponder the implications of their choices. However, the concept also invites existential dread, as it challenges the notion of progress and the finality of life. If everything recurs, then what does it mean to strive for improvement or seek meaning in our experiences? Moreover, eternal recurrence touches on the nature of time itself. In many cultures, time is perceived linearly, with a clear beginning and end, while the idea of recurrence suggests a cyclical nature where beginnings and endings are intertwined. This can shift our understanding of life and death, presenting them not as definitive endpoints, but rather as part of an ongoing journey. In this light, death could be seen not as a conclusion, but as a transition into another iteration of existence, fostering a sense of continuity rather than finality. Exploring this idea further, one might consider how it impacts our relationships with others. If we are destined to live the same moments with the same people over and over, how does that influence our interactions? Would we cherish our relationships more, knowing that each conversation, each shared laugh holds eternal significance. Alternatively, it could lead to artificial intelligence, often referred to as AI, has been a topic of much fascination and debate, especially when it comes to its paradoxes and the concept of infinite loops. One of the key paradoxes in AI is the idea of machines becoming smarter than humans, which raises questions about control, ethics, and the future of human existence. For instance, if we create an AI that can improve itself beyond human intelligence, how do we ensure it acts in ways that are beneficial to us? This paradox touches on the fear of losing control over our creations, as well as the philosophical concerns about what it means to be intelligent or sentient. Another fascinating aspect of AI involves infinite loops, which occur when a program gets stuck in a cycle of repeating the same actions without a way to break free. These loops can happen for various reasons, such as programming errors or logical contradictions within the code. For example, consider a hypothetical AI designed to optimize a task, but it keeps making small adjustments that lead it back to the original state, creating a never-ending loop of changes that yield no real progress. This scenario not only highlights the importance of robust programming, but also reflects the complexities of decision-making in AI systems, where certain algorithms might inadvertently trap themselves in cycles of logic. Then, there's the famous Turing test, a measure of a machine's ability to exhibit intelligent behavior equivalent to, or indistinguishable from, that of a human. The paradox here lies in the fact that even if an AI passes the Turing test, it doesn't necessarily mean it possesses true understanding or consciousness. It could simply be mimicking human responses without any genuine comprehension of the conversation. This raises intriguing questions about the nature of consciousness and whether machines could ever truly think or feel like humans do. Moreover, there's the concept of self-referential paradoxes, such as the well-known liar paradox, which states, "This statement is false." When applied to AI, such paradoxes can lead to situations where a machine's programming leads to contradictory outcomes, complicating its decision-making process. For instance, if an AI is programmed to always tell the truth, but it encounters a situation that requires it to lie, it may become confused and unable to make a decision, illustrating how complex and layered the reasoning processes of AI can be. In addition, consider the idea of ethical programming, where AI must navigate moral dilemmas. This introduces paradoxes related to utilitarianism versus deontological. In decision theory, the concept of infinite loops can have profound implications, especially when considering how we make choices based on uncertain outcomes. An infinite loop, in this context, refers to a situation where a decision-making process cycles endlessly, without arriving at a conclusion. This can occur in scenarios where choices are continuously influenced by previous decisions, leading to a perpetual state of indecision, which can be especially evident in complex systems, such as ecosystems or social structures, where feedback loops are common. When an individual or a group finds itself trapped in such a loop, it can become increasingly difficult to evaluate the consequences of their actions, as each decision may rely heavily on the outcomes of prior choices, creating a tangled web of dependencies. For instance, consider a scenario involving wildlife conservation, where a team must decide whether to implement a specific strategy to protect an endangered species. If their decision-making process involves repeatedly assessing the potential impacts of previous conservation efforts, they may find themselves stuck in a cycle of analysis. Each new piece of information might lead them to reevaluate past decisions, causing delays in action and ultimately hindering their ability to make effective choices. This is particularly concerning in environments where timely decisions are crucial for the survival of vulnerable species, as the longer they remain in indecision, the greater the risk of extinction becomes. Moreover, infinite loops can distort the evaluation of risks and rewards. When decision-makers become overly focused on past outcomes, they may fail to recognize new variables that could influence future results. This can lead to a phenomenon known as analysis paralysis, where the fear of making the wrong choice prevents any choice from being made at all. In nature, this can have cascading effects, disrupting not only the targeted species, but also the broader ecological balance, as each species plays a role in its habitat. Additionally, human behaviors and societal norms can also fall into infinite loops, particularly when it comes to environmental policies. Policymakers might find themselves revisiting the same regulations or strategies without implementing changes, because they are heavily influenced by previous public responses or data interpretations. This can stifle innovation and prevent the adoption of new, more effective methods for addressing environmental challenges, such as climate change or habitat preservation. If decision-makers rely too heavily on past data, they risk missing out on emerging technologies or practices that could lead to better outcomes. The implications of infinite loops extend beyond individual decisions, as they can influence collective behavior and societal trends. In a world where collaborative decision-making is essential for addressing, infinite regression is a fascinating concept that often arises in philosophical discussions, particularly when we explore the nature of existence, causality, and the foundations of knowledge. At its core, infinite regression refers to a situation where a proposed explanation or cause leads to another explanation or cause, which then leads to another, and so on, without ever arriving at a definitive starting point or ultimate explanation. This concept can be illustrated through various philosophical inquiries, such as the question of why there is something rather than nothing, or the search for the first cause of existence. Philosophers have wrestled with the implications of infinite regression for centuries, and it raises several important challenges. One key challenge is related to the concept of causality. For instance, if every cause must have a preceding cause, this leads us to an endless chain of causes, which can be difficult to comprehend. Some philosophers argue that this infinite chain is unsatisfactory, because it doesn't provide a true explanation for the existence of the universe. Instead, they propose the idea of a first cause, or an uncaused cause, which would halt the regress and offer a solid foundation for everything that exists. Another challenge posed by infinite regression is in the realm of knowledge. When we seek to justify our beliefs or knowledge claims, we often find ourselves needing further justification. This can lead us down a rabbit hole of seeking ever more fundamental truths, which raises the question of whether we can ever truly know anything at all. This issue is closely related to epistemology, the study of knowledge, and it forces us to confront the limits of human understanding. In addition to these philosophical challenges, infinite regression can also be seen in various fields, including mathematics and science. For instance, in mathematics, certain paradoxes can arise when we think about infinite sets or sequences, leading to interesting discussions about the nature of infinity itself. Similarly, in scientific inquiry, the quest for ultimate explanations can sometimes lead to an infinite regress of theories and models, each requiring further theories to explain them. A notable example of infinite regression is found in the cosmological argument for the existence of God. Some versions of this argument suggest that everything that exists must have a cause, which leads to questions about what caused the universe itself. This line of reasoning can lead to an infinite regress unless one posits a necessary being, or a first cause, which itself does not require a cause. This theological approach aims to resolve the infinite regress by suggesting a foundation that is outside. Paradoxes play a fascinating, yet often misunderstood role in scientific theories, serving as both challenges and motivators for deeper understanding. In the realm of science, a paradox can emerge when established theories lead to conclusions that seem contradictory or counterintuitive. One classic example is the wave-particle duality of light, which posits that light behaves both as a wave and as a particle, depending on the experiment being conducted. This paradox has puzzled scientists for centuries, prompting the development of quantum mechanics, a field that seeks to reconcile these seemingly opposing behaviors. Furthermore, paradoxes often highlight the limitations of our current scientific models, compelling researchers to refine their theories or even develop entirely new frameworks. For instance, the famous Schrödinger's cat thought experiment illustrates a paradox in quantum mechanics, where a cat in a sealed box is simultaneously alive and dead until observed, challenging our intuitions about reality and measurement. Such thought experiments encourage scientists to explore the boundaries of what we consider to be true, leading to significant advancements in our understanding of the universe. Moreover, paradoxes can also stimulate critical thinking and creativity in scientific inquiry. When faced with a paradox, scientists are often pushed to think outside the box, leading to innovative approaches and solutions. The famous Fermi paradox, which questions why we have not detected signs of extraterrestrial life despite the vastness of the universe, has led to numerous hypotheses, ranging from the rarity of intelligent life to the possibility that advanced civilizations may self-destruct before making contact. Each proposed solution opens up new avenues of research, fostering a rich dialogue within the scientific community. In the context of evolution, paradoxes can also arise, such as the apparent contradiction between the survival of the fittest and the altruistic behaviors observed in some species. This has led to the development of theories like kin selection and reciprocal altruism, which explain how cooperation can evolve among individuals for the benefit of the group. These discussions reveal the complexity of evolutionary processes and the intricate balance between competition and cooperation in nature. Additionally, paradoxes can serve as valuable teaching tools, helping students and enthusiasts grasp complex concepts in a relatable way. By examining paradoxical scenarios, learners can engage with scientific ideas more deeply, fostering a sense of curiosity and encouraging further exploration. For example, the twin paradox in relativity, which describes how one twin ages slower than the other due to differences in velocity, illustrates the counterintuitive nature of time as described by Einstein's theory of relativity, allowing students to visualize infinite loops in the context of computer science and mathematics can seem like an abstract concept, but they have fascinating connections to chaos theory, which studies how small changes in initial conditions can lead to vastly different outcomes. To understand this relationship, we first need to recognize what an infinite loop is. An infinite loop occurs when a sequence of instructions in a computer program continues indefinitely, without a terminating condition. This can be likened to certain systems in nature that behave chaotically, where the outcomes can become unpredictable, despite starting from a seemingly simple set of rules. When we think about chaos theory, we often think of systems like weather patterns, ecosystems, or even the stock market, where minor changes can lead to major differences in results. This unpredictability is a hallmark of chaotic systems, and it can be observed in mathematics through iterative functions, which can behave similarly to infinite loops. Just as an infinite loop runs without end, certain mathematical functions can iterate infinitely, and depending on their initial conditions, they can yield results that are either stable or chaotic. For example, consider the logistic map, a simple mathematical model that describes population growth. When plotted, it shows how populations can stabilize, oscillate, or enter chaotic regimes based on the growth rate parameters, much like how an infinite loop can produce the same output if started from the same input. In this way, both infinite loops and chaotic systems can exhibit stable behaviors under certain conditions, yet can also spiral into unpredictability as parameters change, reflecting that delicate balance between order and chaos. Moreover, just as programmers must be cautious of infinite loops that can crash a system, scientists must also be aware of chaotic behaviors in nature that can lead to unpredictable outcomes. In both cases, understanding the underlying rules or equations is crucial. For researchers, this means that by studying the properties of these iterative processes, whether in programming or in natural systems, we can begin to grasp the complexities of how chaos emerges from simple rules. Interestingly, this relationship between infinite loops and chaos theory extends beyond just mathematics and computer science. It can also be observed in real-world phenomena. For instance, the rhythms of certain ecosystems can resemble the behavior of infinite loops, where species interact in a way that appears constant and predictable, yet is actually subject to chaotic fluctuations due to environmental changes, predation, or competition. In this sense, infinite loops serve as a metaphor for the cyclical nature of life, where certain processes repeat endlessly, yet remain vulnerable to disruption and change. In the realm of nature, ethical dilemmas can arise in many forms, and one intriguing aspect is the concept of infinite loop scenarios, especially when considering conservation efforts. Imagine a situation where a conservationist must decide whether to invest limited resources in saving a single endangered species, like the California condor, or to use those resources to protect a broader ecosystem that supports many species, including less famous ones. This creates a challenging ethical question, as saving one iconic species might bring attention and funding but could mean neglecting a whole habitat that is vital for countless organisms, from plants to insects. The dilemma intensifies when we consider the potential long-term consequences of these choices, where the immediate benefits of saving a single species may not outweigh the broader ecological impact of losing an entire ecosystem. Moreover, infinite loop scenarios often occur in wildlife management, where decisions made today can have repercussions that circle back, creating a cycle of challenges. For instance, if a particular animal, such as the gray wolf, is reintroduced into an area where it had been extirpated, the immediate goal may be to restore balance to the ecosystem. However, this reintroduction can lead to conflicts with local livestock farmers, who may experience predation losses, thus causing them to push back against conservation efforts. In this situation, the question arises, should we prioritize ecological balance or the livelihoods of local communities? The answer is not straightforward, as both perspectives hold significant weight in the discussion, and finding a solution that respects both nature and human interests can be incredibly complex. Then there are the ethical dilemmas involved in climate change, especially regarding how resources are allocated in conservation. In a world where climate change threatens many species and habitats, conservationists might face the choice of focusing on immediate rescue operations, such as relocating endangered species to more suitable climates, or investing in long-term strategies that address the root causes of climate change, such as reducing greenhouse gas emissions. This poses another infinite loop. If we continuously address the symptoms without tackling the underlying issues, are we merely prolonging the inevitable decline of biodiversity? The challenge lies in balancing short-term needs with long-term sustainability, a task that requires careful consideration of ethical principles, scientific data, and community involvement. In addition, there's the ethical concern surrounding invasive species management. When an invasive species is introduced to a new environment, it can disrupt local ecosystems, leading to the decline or extinction of native species. The dilemma arises when considering eradication methods, as they may involve harsh measures. The concept of infinite loops in narrative structure, while often associated with storytelling in film, literature, and video games, also finds a fascinating connection to how we perceive and interact with nature. In narratives, just as in ecosystems, elements can repeat, evolve, and influence one another, creating a complex web of cause and effect. In nature, we often observe cycles, like the water cycle or the food chain, which can be compared to narrative loops, where events or themes recur, building depth and enriching our understanding. This mirroring of infinite loops in both storytelling and natural processes highlights how stories can reflect the interconnectedness of life, illustrating how every action can lead to a reaction that circles back in unexpected ways. When we think about the influence of these loops on a narrative, we can consider how they create a sense of continuity, allowing readers or viewers to immerse themselves in the experience, much like how we immerse ourselves in the rhythms of the natural world. For instance, in literature, an author might introduce a theme of rebirth, which appears throughout the story, echoing the cycles of the seasons, And this repetition can help to reinforce the emotional weight of the narrative, just as the changing seasons remind us of the passage of time and the resilience of nature. Moreover, in nature documentaries, filmmakers often use looping sequences to emphasize the beauty and persistence of life, showing a flower blooming, wilting, and then blooming again, which mirrors the narrative loops that draw viewers in, encouraging them to reflect on the cyclical nature of existence. This technique not only captivates the audience, but also serves as a powerful reminder of how interconnected all life is, urging us to consider our place within these cycles. In video games, infinite loops can serve as a powerful storytelling mechanism, allowing players to experience events multiple times, often with slight variations. This mirrors how in nature, we might encounter the same landscape, but each visit reveals new details, changes in the environment, or shifts in the behavior of animals. Such experiences deepen our understanding and appreciation of both the narrative and the natural world, illustrating how every encounter can unfold differently, despite the familiarity of the setting. The influence of infinite loops on narrative structure also prompts us to think about how we can approach our understanding of ecosystems. Just as a story can be reinterpreted through different lenses, so too can our interactions with nature be seen from various perspectives, encouraging us to appreciate the layers of complexity that exist within both narratives and natural environments. This multifaceted, theoretical physics, a branch that delves into the fundamental principles governing the universe, often grapples with concepts that stretch our understanding of reality. One fascinating area within this field is the study of infinite loop paradoxes, which challenge our perceptions of time, causality, and existence itself. These paradoxes arise when events seem to loop back on themselves, creating scenarios where cause and effect become entangled in a way that defies conventional logic. For example, one might consider the classic grandfather paradox, where a time traveler goes back in time and inadvertently prevents their own grandfather from meeting their grandmother, thus raising the question of how they could have existed to travel back in time in the first place. This paradox highlights a fundamental issue in our understanding of time travel, as it suggests that actions taken in the past can alter the future in contradictory ways, creating a loop that seems impossible to resolve. Another captivating aspect of infinite loop paradoxes is found in discussions about black holes and the nature of information. In a black hole, information about matter that falls in seems to be lost forever, leading to what is known as the information paradox. This paradox challenges the very foundations of quantum mechanics, particularly the idea that information cannot be destroyed. When we consider the implications of a black hole, we confront a situation where matter and energy are seemingly trapped, creating a loop of uncertainty about what happens to the information contained within. Theoretical physicists like Stephen Hawking have proposed various solutions to this paradox, but no consensus has been reached, which continues to fuel debate and research in the field. Moreover, the concept of closed time-like curves, which are solutions to the equations of general relativity, introduces another layer of complexity to our understanding of time. These curves suggest a model of space-time, where an object could return to its own past, creating loops that could theoretically allow for time travel. This raises profound questions about free will and determinism, as well as the nature of reality itself. If one could travel back in time and alter events, would the future still unfold in a predetermined way, or would it branch off into countless new realities? In quantum mechanics, the idea of superposition can also lead to paradoxical situations. In this framework, particles can exist in multiple states at once until observed, leading to scenarios where the act of measurement itself creates a definitive state. This notion introduces a kind of loop in the understanding of reality, where the observer plays a crucial role in determining the outcome of. The concept of infinite possibilities in multiverse theory is a fascinating topic that invites us to explore the very fabric of reality, and it stretches our imaginations beyond what we traditionally perceive. At its core, multiverse theory suggests that our universe is just one of many, possibly an infinite number of universes, each with its own distinct laws, constants, and histories. This idea challenges our understanding of existence, as it implies that every choice we make, every action we take, could lead to the creation of a new universe, where different outcomes unfold. Imagine, for instance, a scenario where you decide to take a different route to work. In one universe, you might arrive on time, while in another, you could get stuck in traffic, leading to a completely different chain of events in each universe. Moreover, the notion of infinite possibilities means that there could be a universe where dinosaurs never went extinct, or one where humans never evolved at all, or even one where the laws of physics are completely different, allowing for things we can barely comprehend, like time travel or the ability to manipulate gravity. This leads to profound questions about our own universe, the nature of choice, and the role of chance. Some scientists theorize that these alternate universes could exist in parallel with ours, separated by dimensions we cannot perceive. The idea was popularized in part by physicist Hugh Everett III in the 1950s, with his many worlds interpretation of quantum mechanics, which suggests that all possible outcomes of quantum measurements are realized in some branch of the multiverse. This perspective not only reshapes our understanding of quantum events, but also raises intriguing philosophical questions about the nature of reality and our place within it. As we delve deeper into the implications of multiverse theory, it becomes evident that the universe is far more complex than we once believed, and each layer of understanding adds to the wonder of existence. While some scientists remain skeptical of the multiverse due to the challenges of empirically testing the theory, others find it a compelling framework to explain the fine-tuning of our universe and the seemingly improbable conditions that allow life to thrive. As we continue to explore the cosmos through advanced telescopes and theoretical physics, the idea of these infinite possibilities encourages us to think beyond the limits of our known universe, igniting a sense of curiosity and wonder about what might lie beyond the stars and how our choices could ripple through the fabric of reality itself. In this grand tapestry of existence, the future of infinite loop research, which is an intriguing area of study, focuses on understanding complex systems, especially in nature, where cycles seem to repeat endlessly, influencing ecosystems, weather patterns, and even the behavior of species. Scientists are increasingly intrigued by how these cycles can provide insights into sustainability and resilience in our rapidly changing world. For instance, researchers are examining the intricate relationships between predator and prey, which often follow cyclical patterns, revealing how these interactions can stabilize ecosystems and allow for biodiversity to flourish. In addition, the study of infinite loops in natural processes, such as the water cycle, highlights the importance of continuous renewal, where water evaporates, forms clouds, and returns to the earth as rain, creating a vital link for all living organisms. Moreover, by analyzing these endless cycles, scientists are striving to apply these natural principles to human systems, aiming to create more sustainable practices in agriculture, urban planning, and resource management. For example, permaculture, which is rooted in understanding natural cycles, encourages agricultural practices that mimic these loops, thereby promoting soil health and reducing waste. Researchers are also looking into the implications of infinite loop theories in climate change, where understanding the feedback loops in our climate system could lead to better strategies for mitigation and adaptation. Additionally, the concept of infinite loops extends to technology, where algorithms and models are developed to simulate natural processes, offering insights that can lead to innovative solutions for environmental challenges. The exploration of infinite loops in quantum biology, a relatively new field, is uncovering how certain biological processes, like photosynthesis, exhibit loop-like efficiency that could inspire new energy technologies. As we look to the future, the integration of infinite loop research with emerging technologies, such as artificial intelligence and machine learning, holds great potential. These technologies can analyze vast amounts of data, revealing patterns and connections within natural systems that were previously undetectable to researchers. The collaboration across disciplines, combining biology, ecology, physics, and computer science, will likely lead to breakthroughs that not only deepen our understanding of nature, but also empower us to live in harmony with it, ensuring that we harness the lessons learned from these infinite loops for generations to come. In essence, the future of infinite loop research is not just about observing cycles, but understanding their profound implications for both nature and humanity, allowing us to learn from the past, adapt in the present, and innovate for a sustainable future. Infinite loop paradoxes in cognitive science are fascinating and complex phenomena that challenge our understanding of thought processes, decision-making, and the nature of consciousness itself. These paradoxes often arise when individuals become trapped in cycles of reasoning, where the conclusions drawn lead back to the original premises, creating a loop that seems impossible to escape. One well-known example is the liar paradox, which states, "This statement is false. If the statement is true, then it must be false. But if it is false," leading to an endless loop of contradiction. In cognitive science, such paradoxes help researchers investigate how humans process information, resolve contradictions, and make decisions under uncertainty. Another intriguing aspect of infinite loops in cognitive science is how they relate to self-reference and recursion in thinking. When individuals reflect on their thoughts, they might engage in a recursive process, where one thought leads to another, often resulting in an infinite regress. This can be seen in philosophical debates, where questions about existence or morality can lead to endless inquiries without a definitive answer. For instance, consider the question, "What is the meaning of life?" Each answer may prompt further questions, creating a loop that can be difficult to resolve. Cognitive scientists study these recursive thought patterns to understand how they influence our beliefs, behaviors, and emotional responses. Moreover, infinite loop paradoxes can also be found in decision-making scenarios, where individuals face choices that seem to lead back to the initial decision, creating a cycle of indecision. This phenomenon is particularly relevant in behavioral economics, where concepts like loss aversion and the paradox of choice illustrate how too many options can lead to paralysis by analysis. When faced with multiple alternatives, people may overthink their decisions, leading them to second-guess their choices and become trapped in a loop of deliberation. Cognitive scientists explore how these loops affect our ability to make rational choices, and how we can break free from them to arrive at more satisfying conclusions. Interestingly, the study of infinite loops is not limited to human cognition, but also extends to artificial intelligence and machine learning. In computer science, algorithms can encounter infinite loops when the conditions for termination are not properly defined. This has parallels in human thought, where unclear goals or conflicting motivations can lead to mental loops. Understanding these patterns in both humans and machines can provide insights into improving decision-making processes and enhancing problem-solving skills. In addition, the concept of infinite loops touches on the nature of consciousness itself, raising questions about self-awareness, and infinite loop paradoxes can be fascinating yet perplexing, especially when we consider their implications in both mathematics and philosophy. To teach these concepts effectively, educators often turn to a variety of educational approaches that engage students' critical thinking skills and promote deeper understanding. One approach is through the use of visual aids, such as flowcharts and diagrams, which can help illustrate the cyclical nature of these paradoxes. By mapping out the different scenarios that lead to a loop, students can better visualize how one statement can lead to another, then back to the original, creating an endless cycle that can be difficult to grasp without a clear representation. Another effective method is incorporating hands-on activities, where students can explore paradoxes through interactive simulations. For instance, teachers might use coding exercises that involve loops, allowing students to see firsthand how these constructs function in programming languages. This not only makes the concept more tangible, but also connects abstract ideas to real-world applications, fostering a more profound appreciation for the topic. Discussions and debates can also be valuable, as they encourage students to articulate their thoughts on paradoxes, challenge each other's viewpoints, and explore the philosophical implications of infinity and logic. Incorporating storytelling can be another powerful approach. By presenting paradoxes through engaging narratives, educators can capture students' imaginations, allowing them to relate to the concepts on a personal level. For example, a story about a character who encounters a scenario that leads them into an infinite loop can spark curiosity and stimulate discussion about the nature of reality and perception. This narrative technique not only makes the learning process more enjoyable, but also helps students internalize the concepts by connecting them to human experiences. Additionally, integrating technology in the classroom can enhance the learning experience. Using computer simulations or online platforms that allow students to manipulate variables in a controlled environment can provide immediate feedback, enabling learners to experiment with different outcomes and better understand the underlying principles of infinite loops. This interactive approach can cater to different learning styles, ensuring that all students have the opportunity to engage with the material in a way that resonates with them. Furthermore, encouraging collaborative learning can also be beneficial. Students can work in groups to tackle paradoxical problems, allowing them to share ideas, debate solutions, and learn from one another. This collaborative environment can foster a sense of community and shared inquiry, which can be particularly effective when grappling with complex ideas that may initially seem daunting. Lastly, providing historical context can enrich the learning experience. Exploring the origins of infinite loop paradoxes, such as those posed by cultural perspectives on infinite loops, can be quite fascinating, as they reflect how different societies interpret and interact with concepts of time, cycles, and continuity. In many Eastern philosophies, for instance, the idea of cyclical time is prevalent, contrasting sharply with the linear view often held in Western thought. In cultures influenced by Hinduism and Buddhism, the cycle of birth, death, and rebirth, known as samsara, embodies the concept of an infinite loop where life is seen as a continuous cycle rather than a straight path leading to a definitive end. This perspective encourages individuals to focus on their actions and their consequences, as every action can influence future lives, creating a profound sense of responsibility and mindfulness. In contrast, Western cultures tend to emphasize a linear progression of time, where events are seen as a sequence leading toward a specific goal or conclusion. This linear view can be seen in various narratives throughout history, where the focus is often on beginnings and endings, with less emphasis on the cyclical nature of experiences. However, even in these cultures, elements of infinite loops appear in myths and stories, such as the concept of a hero's journey, which often involves recurring themes and challenges that the hero must face repeatedly, showcasing the idea that growth and learning can come in cycles. In the realm of mathematics and computer science, infinite loops take on a more technical meaning, referring to a sequence of instructions in a program that repeats indefinitely. This concept has philosophical implications as well, raising questions about the nature of existence and consciousness. Some modern thinkers draw parallels between these technical infinite loops and the philosophical inquiries into whether life itself might be akin to a program running in an endless cycle, prompting discussions about free will, destiny, and the nature of reality. Art and literature also reflect cultural attitudes toward infinite loops, with various narratives exploring themes of repetition and continuity. For example, in literature, works like 100 Years of Solitude by Gabriel Garcia Marquez highlight the cyclical nature of history and family, suggesting that certain patterns tend to repeat themselves regardless of individual choices. This artistic representation resonates with the idea that, just as nature has cycles such as seasons and life cycle, human experiences can also reflect repeating themes and lessons. Moreover, in many indigenous cultures, there is a strong emphasis on harmony with nature, where the cycles of the earth, such as the changing of the seasons or the life cycles of plants and animals, are respected and understood as part of a greater whole. These cultures' infinite loop paradoxes, which are often seen in philosophy and mathematics, present fascinating challenges that extend beyond their immediate logical implications. These paradoxes, such as the famous liar paradox, where a statement refers to itself in a manner that creates a contradiction, force us to rethink the nature of truth and meaning. As we dive into the future philosophical implications of these paradoxes, we find ourselves at the intersection of logic, language, and the human experience. The very idea of a paradox can shake the foundations of how we perceive reality, pushing us to question what can be known and how we come to understand the world around us. In a world increasingly driven by technology, the implications of infinite loop paradoxes could extend into artificial intelligence and machine learning. For instance, if we create algorithms that attempt to resolve these paradoxes, we may encounter unforeseen issues that challenge our understanding of consciousness and reasoning. As we program computers to engage with complex philosophical questions, we must consider whether machines can navigate these paradoxes, or if they will simply reveal the limitations of our own logical frameworks. This raises questions about the nature of intelligence and whether it can truly replicate human thought when faced with the limitations of self-reference and contradiction. Furthermore, infinite loop paradoxes could impact ethical discussions in the future, especially in scenarios involving moral dilemmas. Consider the classic trolley problem, where one must decide whether to divert a runaway trolley onto a track where it will kill one person instead of 5. Introducing paradoxical elements could complicate these ethical decisions, leading to a deeper examination of moral principles. Can a paradox reveal the limitations of utilitarianism, or challenge the absolutes of deontological ethics? These inquiries may lead to new ethical frameworks that recognize the complexities and nuances of real-life situations, which often defy simple categorization. In addition, the concept of infinite loop paradoxes invites us to examine our communication and language. Language is inherently limited, and paradoxes highlight the challenges of expressing complex ideas. As we evolve our language to accommodate new thoughts and technologies, we may find that paradoxes serve as a catalyst for linguistic innovation. The way we construct statements, the meanings we attribute to words, and our understanding of context could all shift as we grapple with the implications of paradoxical reasoning. This could lead to richer, more nuanced conversations about existence, identity, and the human condition. Moreover, in the realm of metaphysics, infinite loop paradoxes push us to confront the nature of reality itself. If